Welcome. In this video, we will take a look at a few more applications with our optimization section. Let's jump into the first example. So a manufacturer has been selling 1,300 television sets a week at $360 each. A market survey indicates that for each $24 rebate offered to a buyer, the number of sets sold will increase by 240 per week. So there's quite a bit of information here to consider. So let's go ahead and jump into the first part, and then we'll try to analyze and put together the data. So we want to first find the price function. We'll call that P of X, where X is the number of television sets sold per week. And they give us a little hint here to kind of write this out in two steps. You can write out the two functions in terms of the number of rebates first, and then use these to create your price function in terms of number of TV sets sold per week. So let's go ahead and consider doing that. We'll first try to create a function with the price, and then function with the quantity of TV sets sold in terms of rebates. So let's start with considering the first equation. So the first equation we can consider is the quantity equation. I'll just call this X. So again, X is the number of TV sets sold per week. And we were told in the problem statement that we first are selling 1,300 TVs at our current price. So we would say right now we're selling 1,300, but for every rebate, we should be able to increase our sales by 240 television sets. So I'm going to kind of pair up these two items here. Let me do that for a quick second. That's our current output or quantity. And we should be able to gain 240 sets per rebate offered or per discount. So we could say, based on that, we could add to this quantity 240 per rebate, and I'll call that R. And this will be just the number of rebates. And again, those rebates are $24 a piece. So we'll have to keep that in mind for later. So that would be a quantity equation. The next thing we could do is a price equation. So let's do a price equation. The price is currently sitting at $360 per set. So if we go to consider the number of television sets, current price would be $360. And for each rebate, we're going to discount the price by $24. So those two items we can pair up with a price equation. So we would say that currently we have $360 per set, and then we're going to subtract, this is important since we're discounting our price for every rebate. So that would be negative 24 times R, that would be the discount that we get for our rebates. So for instance, if we had only one rebate, we'd subtract the price by 24. If we had two, we could subtract the price by 48, and so on. So both of these items are now in terms of the rebates applied. We would like to go out and solve for, again, the P of X function. So to do this, we have to combine these two functions carefully. So let's take a look. If I go ahead and try to solve for R in my first equation, I could do some substitution and make the P function in terms of X, and that's my goal. So let's do a little bit of work on that X equation. We could say, rewriting that quantity equation, we have that X minus 1,300 is equal to 240 R. And dividing by 240, we get that X minus 1,300 divided by 240 is equal to the value of R. So that's the rebates in terms of our quantity. This is the quantity here that we could go ahead and substitute into my price equation. So here's where we're going to get the P of X function. We'll still have that 360 from before minus 240, or sorry, 24, and then times our X minus 1300 divided by 240. We certainly can go ahead and try to break this down a little bit. I think that would be helpful, specifically for our next step. We do have the P of X equation, but let's go ahead and try to simplify this as much as we can. So taking a look at the product here, we can take our 24 and 240, cancel those out, 1 over 10. And then as we rewrite this, we can state that this is going to be P of X is 360. We'll have minus X divided by 10, which is still there. So minus X divided by 10. And then we'll have a double negative when we distribute this. So 2 negatives will make a positive. And then we'll have 1300 again divided by the 10, which is 130. So we'll still have 130 here. So adding some like terms here, I think we can come to our final result. We'd have that P of X, I'll write on the side here, and I'll try to make this a lowercase. This is a lowercase p of X for the price, is going to be 360 plus 130 would be 490. And then we'll do minus X over 10. And again, that's going to be the price of our televisions based on the quantity. So we'll leave that as our result for part A. Let's move on to part B. Part B asks us to find how large of a rebate should the company offer to a buyer in order to maximize revenue. So you want to think about revenue now. And a few ways we've talked about revenue is the price times the quantity. And I think this is going to be helpful here as well, because we know the quantity here is represented by the value of X, or the variable X, and our price is this P equation. So that's the price is dependent on X itself. So we can say that revenue is going to be the price, we'll call that P of X, times the quantity itself, that would be X. So let's go ahead and simplify that revenue function and then see if we can maximize it. So revenue is going to be my price equation times my quantity X, that's the number of television sets sold. Doing a little distribution, we can have that our R revenue, we could call that R of X, or just R here, is going to be 490 X minus X squared over 10. Now that we have our revenue function, we could go ahead and think about maximizing this value. Notice that this is also going to be kind of a downward facing parabola based on the algebraic expression. And so we're really thinking about what's that peak or vertex point of this parabola. So if I go to take my derivative, I'll take the R prime here. We'll have 490 minus, if I bring the 2 down, raise X to 1, we would get really X over 5 to remain. So 490 minus X over 5. We want to set this equal to 0. to find where we have our maximum value. So that would be 490 minus x over 5. If we rearrange this by adding x over 5 to both sides, we'd have x over 5 equals 490, or x is going to be equal to 5 times 490. And with that result, we should get a final result here. Looks like to be 2,490 TVs. Now, this is a good result, and this is true, but it's not necessarily what we were searching for. We want to be careful to consider what they're actually asking for. We want the number of rebates that we need to maximize the revenue. And this is the number of TV sets sold that will maximize revenue. So we're pretty close. We just have to relate this back to the idea of the rebates. So let's consider how quantity and rebates were related. Quantity and rebates were related based on our first equation. So if we looked here, we could solve for the number of rebates by considering that first equation. So taking a look at this, we have that R, the number of rebates here, was equal to x minus 1,300 divided by 240. So let's go ahead and use that to our advantage and consider how many rebates we're going to have. So if I use that top equation, I have 2,490 minus 1,300 divided by 240. This is going to give me the number of rebates. So R is going to be equal to this. That's the number of rebates. If I do a little bit of work in the numerator here, we'll have 1,190 divided by 240. We can cancel out the zeros there to reduce down to 119 over 24. I'm going to stop here and just consider, well, if this is the number of rebates, remember this R is the number of rebates. It wants how large of a rebate in dollars, how large of a rebate. Recall that each rebate was $24 in size, each rebate. And so if this is R, to get the size of the rebate, we actually just want to multiply by $24. And so the size of the rebate we can actually represent as the number of rebates, R, times 24. And in this case, we'd have 119 over 24 times 24, which gives us the final result of the size of $119. So this is the size of the rebate that we're going to need to maximize that revenue. In other words, if we looked back at the original price, $360 was our original price. And so if we took our original price, subtracted 119, this would be $241 for really the price of the TV that would maximize our revenue. So that's not really asked here, but you can kind of take that next step and consider the actual price of the TV that would maximize our revenue. So 119 would be the size of the rebate. That's the answer to this part B. We have one more part to consider here, and that goes to the idea of profit. So if the weekly cost function is the C of X function given, how should the company set the size of the rebate to maximize profit? So this is a little bit different. Now we're incorporating another function, which is cost. So if we go for this cost function, there's another way to represent here our profits, and we did that by considering the profit, P of X, is represented by the revenue, we'll call that R of X, subtract our cost, C of X. So we knew the revenue function from the part B. They give us a cost function, and now we're going to consider how we might maximize this quantity of profit. So going back up here, we're going to take this R of X function. We're going to use that in conjunction with our cost function. So let's go ahead and dive into this one. We have the revenue function. I'm going to go back to our black pen. We have 490x minus the x squared over 10. That is our revenue, and we're going to take that and subtract our cost. So this is our cost for production. And again, that's our P of X function. So let's go ahead and simplify this as much as we can, and then we'll go ahead and take its derivative, set it equal to 0, and again, find a maximum value. So taking a look at this, we'll have a distribution of this negative. We'll have negative 78,000 and minus 120 times x. So if we look at the light terms here, we'll have 490x minus 120, which will give us 370. So we have P of X. We'll still have this leading term of the squared, so we'll maybe put this in front. We have negative x squared over 10. If we have the 490 and negative 120, that becomes positive 370. And then the last term we can highlight here would be our constant. So that would be negative 78,000. There we go. All right, now we're ready to just consider this derivative. We'll call the P prime of X derivative. P prime of X. If we take this derivative, the start will be very similar to the revenue. So we'll have negative x over 5 plus 370. This looks like it is a linear function, so we'll have only one solution here. If we set this equal to 0, we can add x over 5 to both sides. Multiply by 5 on both sides to get my quantity. And this quantity is going to end up being 1,850 if we take that product. So that's the number of TVs there. Again, we're not really concerned with the number of TVs that is needed to maximize profit. We want the size of the rebate again. So we're going to have to walk through converting this X value to the size of the rebate one more time. So let's go ahead and try to do that. We'll just kind of drop down below on the next page to figure that out. Again, we're using the same equation as before up here. So we're taking our quantity here, subtracting 1,300 and dividing by 240 to get our rebates, the number of rebates. So I have 1,850, subtract 1,300 and divide by 240. Again, this is going to be the number of rebates, R. So we can go ahead and try this out. We'll have looks like 550 divided by 240. And again, we can reduce this down to 55 over 24. So when we consider the size of the rebate, again, the size of our rebate is going to be $24 times the value of R. And so we'd have 24 times 55 over 24. So that's our size of our number of rebates. We cancel out those 24s and we'll get $55 rebate to actually maximize our profits. So with the added constraint of the cost, we actually don't want to give too much of a rebate. We'll actually have to only give a $55 rebate to maximize profit. And that's really what we should be after, is maximizing profit instead of just revenue itself. Okay, so that would be the completion of Part C. Let's go ahead and jump into our next question. The next question involves, again, a kind of a variable price on a service. So this says that Jackie is a chemistry student and she tutors on the side. She currently charges $30 per hour tutoring science and has 7 clients meeting once a week. After adjusting her rates up and down for the last year, she found that she gained a client for every $2 decrease in her hourly rate. At what rate should Jackie tutor at to maximize her revenue? What will the maximum revenue be? Okay, so little typos here, but we can consider kind of what the question is asking here. She is currently offering tutoring service that's $30 per hour. She currently has 7 clients. And she's considering a price decrease here. For every decrease in her rate by $2, it says, she should be gaining 1 client. She wants to know where is kind of that happy medium where she's going to create the most revenue based on that relationship. So let's start with the idea of revenue to start. Her revenue, again, is going to be her price times quantity, and in this case, quantity is the number of clients she has, so P times Q. So if we consider the P times Q here, well, currently her price is $30, but we're considering for every discount, we'll maybe just call this D as the number of $2 discounts. So this is the number of $2 discounts. Well, for every $2 discount, she anticipates gaining 1 client. So let's consider the price here. The price, we could say, currently is $30, but for every discount she gives, it's going to go down $2. So I would say it's going to decrease 2 for every discount. And again, D is going to just measure the number of discounts here, not the dollar amount. Next, we can consider the quantity. Well, currently she has 7 clients, and she is going to gain 1 client for every discount she makes. So we could say that we can add 1 client. We could put a 1 there if you want, for every client she gains. So that would just be 1D, or you could just put a D. For every discount she adds, she should gain a client. So this revenue function here is actually a function of the number of discounts. So let's go ahead and multiply through with this. and get a nice equation for revenue, and then we'll see if we can go ahead and maximize that. So doing a little bit of foiling here, we can go ahead and try getting our revenue function. So that would be revenue is 30 times 7 plus 30 times D. And we'll have our bottom products, negative 2D 7 and times D again. That would be negative 14D and then negative 2D squared. If we go to add like terms here, looks like those middle terms will reduce down to 16D. So we have the revenue is going to be 210 plus 16D minus 2D squared. So here again, we have a nice revenue function to work with. We'd like to maximize this. And we'll find the number of discounts to maximize. And then we'll have to consider what her actual rate is going to be in terms of price. So taking the derivative r prime, we'll have 16 minus 4D. And again, we have a linear function here, so there should be one maximizing value. Set this equal to 0. And we'll have 4D is equal to 16, or the number of discounts is going to be equal to 4. Now, this doesn't answer our revenue question. What rate should she tutor at to maximize her revenue? But it gets us pretty close. So let's consider what we have to do to finish this off. If I wanted to maximize my revenue, what would the actual price be, or my rate? Well, each of these discounts is worth $2. So if I want my total size of my discount, the size of the discount again is going to be the value of D, which is 4 discounts for $2 a piece. So the total discount here is actually going to be $8. So her price that's going to maximize this revenue is actually going to be her current price, $30, subtract $8. And so she should charge $22 here to maximize her revenue. Another thing is, what is this maximum revenue going to be? Well, let's consider the actual revenue equation. If I look back at the revenue equation, I can go ahead and maybe pick out just this right here. Here's my revenue equation. This is based on the number of discounts, so we could go back and just use D as our input and say what is really R evaluated at 4. So we'd have 210 plus 16 times 4 minus 2 times 4 squared. And when we do this, you can plug this into your calculator if you'd like to consider what's the actual revenue. And this revenue would actually become $242 for the total revenue. So that would be the maximum revenue she could get with her tutoring each month. Let's go ahead and take a look at one more example together for this section. This says that the Arizona State University newspaper, the State Press, sells for $1.50 per copy. The cost of producing X copies of a given edition is given by C of X equal to 70 plus 0.1x plus 0.001 x squared. Let's first compute the revenue and profit when the school sells 500 copies. So we want revenue and profit for 500 copies. Let's jump into that. If I wanted to consider the revenue and the profit, let's start with the revenue. We'll call that R of X. Well, we aren't necessarily given an explicit revenue function, but we do know that we're selling our copies for $1.50. So every copy, in other words, is worth $1.50 times the number of copies. That would actually create our revenue function right there, just based on our sale price. So if I consider the revenue at 500 copies, we can find that by just inputting 500. So we have 1.5 times 500, or 1.5 times 500, which is going to be 750. So that would be our revenue for 500 copies. We can now consider, well, what is the profit for 500 copies? So below here, let's go ahead and consider what a profit function might look like. So we have the P of X is going to be equal to my revenue minus my cost. So we knew our revenue function is just 1.5 times X minus our costs, which are given below or above. So we have 70 minus 0.1x plus 0.001 x squared. Looks like we'll need to simplify this a little bit. We will have a distribution of a negative here, so that'll become a negative, positive, and then we'll have a negative when we distribute. And we can rewrite this one time here for our profit function. We'll have two terms that combined. That would be the 0.1x and the 1.5x. Those are going to be added together. Actually, it should be subtracted. Let's go ahead and check our math here. These should be a subtraction because it started as a sum. Let's go ahead and make sure that is right. So that started as a sum, we distributed, should be a minus sign there. So each of those terms should be negative. So subtracting those, we'll get a 1.4x, negative 70, and then we'll also have a negative 0.001 x squared. Now, in this case, we just want to find what is the profit at $500, or 500 copies, excuse me. And so now we just want to input this into our profit function. So P of 500, again, we'd have 1.4 times 500 minus 70, and then we'll have subtract 0.001 times 500 squared. When I consider that profit there, you can plug that into your calculator and find your result there. Believe we should get a profit here of $380. So there's our profit. So revenue of $750, that's what we actually just make in sales, but incorporating our costs, we only profit $380. Let's consider part B. This is computing the marginal revenue. So marginal revenue, when we see marginal, think of the rate of change or the derivative of that quantity. So marginal revenue, in our case, would just be R prime of X. So for us, marginal revenue would really be just 1.5. So considering marginal revenue, when 500 copies are sold, well, we would just consider it's still $1.50, right? The rate of change here is still $1.5 per paper. Again, when revenue is just in dollars up there, as well as the profit. And so when we do R prime of 500, well, since this is constant, we just get, again, $1.5 dollars per paper. Say dollars per paper as well. If I wanted to consider computing the marginal profit, it's a little bit different. We will have some variability there. We know our profit function from above. Let's go ahead and box that. So the marginal profit, we can say is again going to be P prime of X. We can take its derivative. We have 1.4 minus, if we multiply by 2 on that last term, the 70 goes away as a constant, and we're left with negative 0.002 times X. We go ahead and consider setting this equal to 0. Actually, not setting this equal to 0. We just want to consider the marginal profit when 500 copies are sold. So we just want to do P prime of 500. So P prime of 500 will have 1.4 and then minus 0.002 times 500. When we calculate this result, we should get about 1.3 or $1.30 per paper. Again, that's the rate of change of the profit when we are making 500 copies or selling 500 copies. We should be profiting $1.30 per paper at that moment in production. The last thing we want to consider here, and this will finish up this video, is how many copies must be sold to maximize our profit. So now we want to consider, again, that marginal profit function we just found. And if I go ahead and set this equal to 0 to maximize my profit, I'll find the production level here that will maximize. So we can add our decimal times X. That would be 0.002X equaling 1.4. And then X is going to be 1.4 divided by 0.002. And this should give us, if we go ahead and move our decimals, you can see, even doing this on hand, moving 3 times to the right, moving 3 times to the right would give us 1,400 divided by 2, which is going to give us 700 newspapers. So that's the production level there, or the number of copies that we want to make to maximize our revenue. So we'll leave it as 700 papers. So hopefully this was helpful. In the next video, we will consider some geometric applications, looking at different shapes to maximize areas and surface areas. Thanks for watching.